Okay, so when we talk about transition metal complexes, there's a couple of things that happen which are both very beautiful but warrant a lot of work in terms of explaining. So that's how we developed the crystal field theory. But what were these observations that we see with transition metal complexes? Okay, so first let's talk about color. So if I take something like my cupric complex here, so this is going to be what? Tetra, aqua, copper, 2 ion. It's actually a very, very light blue, and actually this isn't such a bad color for it. It's about right. Very light blue. But when I add in aqueous ammonia, like concentrated ammonium hydroxide, I form my tetraamine copper 2 complex ion. So I have formed this complex when I originally had this complex. When that happens, I get this very, very, very dark royal blue solution. So there's a color change to it. Now, what's causing that color change we'll go into in just a moment. But when we talk about that, just so you know, it hasn't anything to do with the change in the geometry. I didn't go from square planar to tetrahedral. I'm square planar and I stay square planar. All I've done was change my ligands. So we need to be able to understand and explain the changes in color. Now, just so you know, when we talk about the changes in color and we talk about color of transition metal complexes, remember this is an absorption. When we look at it, when we look at these complexes, we're talking about absorption spectrum. Okay, so in other words, as I'm shining my light through my sample, my sample absorbs, okay, certain wavelengths. Okay, and what we see with our eyes is not those wavelengths that were absorbed, but all the wavelengths that weren't absorbed. All wavelengths not absorbed. Okay? So that's what we're looking at when we see these changes. So if I see like blue, what does that mean for the solution? What color is the solution absorbing? And we look at the color wheel to find out. And if we separate our color wheel, we'll start here, 750 nanometers. And here is 400 nanometers. Okay, this is 560. Then this is the Roy G, and the Viv, but the indigo is right in between here. Okay, so why is this important? So here's the thing. If I see a blue solution, the color that's absorbed is orange. Okay, so when I see for my copper 2 solutions, those two complexes, they're blue, that means it's absorbing an orange. So what happens if I see, like on a plant, the leaves are green. So I see green. What wavelengths are my plant leaves absorbing? They actually absorb in the red region. Okay? So when we look at the color wheel, what we're saying is that when we see a color, what's being absorbed is opposite on that color wheel. Okay? Now, what about, so our whole goal is to understand why we're seeing changes in color. Last, magnetism. So we'll briefly talk magnetism. So these are all these observations that we need to explain. For magnetism, it turns out this is my hexacyanocobaltate 3 anion. Okay? So it turns out that this is diamagnetic. Has no unpaired electrons. Okay? However, what about this one? I have a hexafluorocobaltate 3 anion. And this one's paramagnetic. Okay, it has 4 unpaired electrons. For metal. Okay, so why is that? And is there a way that we can understand and explain this so I can give you a formula and you can predict whether it's going to be diamagnetic or paramagnetic? And so, in order to explain and understand what's going to happen here, we're going to refer to crystal field theory. Okay, so that's what we'll do next. Alright, this gives some discussion to crystal field theory. We talked about how transition metal complexes have various colors and they have magnetic properties. And these properties are related to their d electrons. So we need to find a way to understand how that happens. Now if you look at a complex ion, the forces in there, there's an attraction between your ligands, the lone pairs on the ligands, okay, whether they're neutral or anionic, but there's a attraction between the metal ion, which is positively charged, and your ligands. Now, there's also a repulsion, and that's between the d electrons and the ligands. Because remember, as the ligands approach my metal ion, basically they're going to encounter d electrons as well. So, what we're going to do is we're going to focus on octahedral first to explain crystal field theory. So, our first geometry that we study will be octahedral. Okay? And normally, when we look at a free metal cation, okay, and we're just looking at my orbitals, they should all be degenerate. Okay, so then when I have my cation with ligands, okay, they go up in energy. But here's the thing. This gets split into two different sets. Okay? This is a T2 set, and this is the E set. Now, what is the T2 set? What is the E set? So, let me just draw one. I don't have enough space, so what I'm going to do is I'll do the T2 set first. 2, 3. This is my X, this is my Y, those are my Z coordinates. Okay? And now that you have the X, Y, and Z coordinates, remember what we have is this. If we look at my D, X, Y, right? Then that basically is going to be, it's almost like a clover leaf in the X, Y plane. Okay? If I look at D, X, Z, then it's essentially my clover leaf in the XZ plane. Okay? And then we have DYZ. And that's my clover leaf in the YZ plane. Alright, so sorry about that. DXY, my clover leaf in my XY plane. DXZ, the orbitals, the D orbitals, will be a clover leaf in the XZ plane. And the DYZ is going to be like this. It's going to be my orbitals that look like a clover leaf along my YZ plane. If you look at the orientation of where my ligands are, okay, my ligands, octahedral, will be there. And you can see there's no direct interaction. Okay, it's like if these are my two lobes, this is where the ligand is. Okay, so it's right in between. Likewise here, likewise there. So my T2 set is composed of DXY, DYZ, DXZ. These are all the clover leaves where my ligands are not directly in line. Now let's take a look at my other two D orbitals. If we look, let me draw my coordinates again. Okay, remember that's X, Y, and Z. So, if I look at D, X squared minus Y squared, okay, here's X, here's Y, and you get your clover leaf, but it's right on my axes, okay? If I look at my other orbital, which is D, Z squared, it's that one, it's along the Z axis, it's got that little itty bitty love handle right there, okay? So in this case, for the E set, since all of my D orbital lobes, okay, are along an axis, if my ligands in octahedral are here, then they're going to have a direct repulsion because they're along the same axis. Likewise, I have a direct repulsion here. So my E set, once I put a ligand in, my E set, you can tell because of the coordinate system, is going to be higher in energy because of the repulsion. Okay, hold on. One moment. Okay, so now that we know that there's a difference in energy between the T2 set and the E set, then we can now explain the colors and how to explain that. So it just so happens that when we actually look at the energy difference between our T2 set and our E set, this difference in energy corresponds to visible light. Okay, so what that means is if I have an electron in my T2 set and I shine light on it, then what will happen is that that electron gets excited and it goes into its excited state, which it bumps up to the E set. So this is my excited electron. And this is my ground state. Electron. And again, the amount of energy that requires this is actually within the region of visible light. We call this a d-d transition because I'm going from a d orbital to a d orbital. So we're looking at d-d transitions when we look at complex ions and their color changes. Okay, so when we talk about it, let's talk about what happens when we change this difference in energy. And that difference in energy we refer to as just delta. Okay? So, when we look at the subset of ligands, okay, so chloride, water, ammonia, ethylene dilene, nitrite, okay, N bonded, and the cyanide group. Okay, so as I go across, this is increasing delta. In other words, the difference in energy okay, between the T2 set and E set increases going to the right. Alright, so these are called weak field ligands. Okay, and these are called strong field ligands. Alright, so when we're talking about these DD transitions, we need to know what ligands we're working with. Okay, so let's take a look at what happens. All right? So, we're going to take a look at two possibilities. Okay? So what are the two possibilities? Okay? So, this is energy. Okay? Then what we need to look at is this. I have my T2 set and I have my E set. Okay? And we need to take into account these situations. Alright? So let me just go ahead and 3 times. Alright? So, when you look at D3, okay, that's what you're going to get. T2 is lower. We're doing the lowest energy to higher energy approaches. These are just my d orbitals. Okay, so when I look at D3, I just fill in the 3. But the question is, where do you put the 4th? Where do you put the electron for D4 ions? Okay, and this is where we have to take into account the weak field and the strong field. Okay, so when we put in our 4th electron, there are 2 places we can put it. We can put it in the E set, or we can put it in the T2 set. What determines that? So what determines that is the repulsion of electrons versus delta. Okay, so if this is a large delta, just put it over here. This has a large delta. This is a small delta. Okay, so when I put in my electron for a D4 electron, 1, 2, 3. If it's a large delta, okay, then what happens is the repulsion is less than delta. In other words, I would rather be here than spend all the energy to go up here. So you pair it up. What happens on this side? Okay. If it's a small delta, then the repulsion from having 2 electrons in the same orbital is greater than delta. If that's the case, then I would do 1, 2, 3, and I would put it up here because that's more energetically favorable. Okay, so when my repulsion, by adding that 4th electron, these are both D4, is larger than the difference in energy between E and T2, then I put it up in E, because that requires less energy. This, because it's high, it's called a high spin complex. Okay? A high spin ion. What happens if this delta is so large, then it doesn't require as much energy to put it in the same orbital here in T2 than it takes to put it into the E. So they're all in the lower area, so this is called a low spin complex ion. Okay, so when we look at the ligands for being whether they are weak field or high field, remember the delta increases with high field, the delta is small with weak field. So it will tell you for the octahedral, it will give you an idea how to predict whether you're going to have a high spin complex or a low spin complex. Okay, so let's go ahead and let's take a look at an example. Okay, let me give you these two. We had mentioned previously, okay, hexafluoro cobaltate 3 ion and hexacyano cobaltate 3 anion. Go ahead. And what happens here is this. Remember, one of them had magnetic properties and the other was diamagnetic. So, I can't remember which. Let's go ahead and take a look and see if we can predict it. So remember, fluoro ligands, the fluoride, this is a weak field. So delta is small. Okay. The cyano, or the list that we talked about, is a strong field ligand. So the delta is large. Okay, so let's take a look at my D electrons. So cobalt, all right, has 27 electrons, and it's going to be just cobalt. This is for cobalt. Argon, okay, and 4s2, 3d, 1, 2, 3, 4, 5, 6, 7. Okay, so cobalt 3 plus. All right. Remove this. Oops. Okay. So 1, 2, 3. So it's 3d6. Okay. So let's see what happens now. Okay. So here, if we're looking only at my d orbitals now, I have my ligands, so I'm going to have my T2 set and my E set. And I made delta small. Here, I have my T2 set, and I'm going to have my E set. I'm going to have a much larger delta. Okay, so here, delta is large. Okay, and here, delta is small. All right, 6 electrons. So, for my hexafluorocobaltate 3, I have 1, 2, 3. Since delta is small, it's going to be a high spin. 4, 5, 6. Okay. With the delta here, with my hexacyano, since we know the cyanide is strong field and delta is large, then we're going to be low spin, right? 3. This is too large to overcome, so 4, 5, 6. So it turns out, this one, being a low spin complex, all my electrons actually are paired. So this one is diamagnetic. Okay? And for the hexafluorocobaltate 3, I have 4 unpaired electrons per metal ion. This one's definitely paramagnetic. Okay? So by understanding crystal field theory now, then we can go through and determine what is diamagnetic and what is paramagnetic. Okay, so let's take a look, all right, at a few other examples. Okay, so what are my other examples? Well, we've been doing octahedral. Let's talk about tetrahedral and square planar complexes. Okay, so in tetrahedral, and square planar, okay, basically this is kind of hard to draw. I think I'll insert your picture for tetrahedral. But for tetrahedral, okay, if this is my D for my free metal ion, then in this case, for tetrahedral, my T2 set is here, is a higher energy than my E set, and my delta is always small. Okay, it's always smaller than what you're going to see with an octahedral. Because of that, we're always going to be in a high spin situation. So let me give you an example, okay, of a tetrahedral that we can use. All right, let's see if I can find one. Let's try this. So this is going to be tetrafluoro manganate 2 anion, right? So manganese, Mn has 25 electrons. Okay, so manganese is basically argon, 4s2, and 1, 2, 3, 4, 5, 3d5. We know that my oxidation state for this manganese is going to be manganese 2, which means it's going to be argon 3d5. Okay, so when we do that, let's fill up. This is a tetrahedral complex. Okay, let's fill up my 5 electrons. So 1, 2, 3, 4, 5. This is definitely paramagnetic. Okay. Now let's try something like square planar. Okay, so this is my example for tetrahedral. Let's look at the next example, square planar. The reason I put them both together is, remember, both tetrahedral and square planar have 4 ligands. Okay, so let's take a look at something like this, square planar. And if we look at my orbitals, what we find is this. 1, 2, 3, 4, 5. Okay. So remember, it'll be X, Y, and Z. So now if I do dxy, 1, those are my lobes, dxz, dyz, dx squared minus y squared, and then dz squared. Okay, so let's go ahead and put in our ligands. Okay, so here's my ligand. It's going to be 1, 2, 3, 4. That's my square planar. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. Okay. So if we draw our energy diagram, okay, and you can see with the overlap of the dx squared minus y squared is the highest energy. Okay? dxy, they're in the same plane. They're not directly related, but they're in the same plane. Okay? This is not in the same plane here. That's not in the same plane there. I have this little love handle, so that's why it's going to give this more repulsion. And these two they're both in the z-plane, and that's why everything in the z-plane is of lower energy. So when we look at square planar, okay, then this is what we're looking at in terms of the orbitals, the d orbitals, okay, with the ligand. So let's take a look and let's pick, let's say, platinum, Cl4, 2 minus. Okay, so if we look at platinum, okay, so platinum is way over here. So we're looking at basically xenon. Okay, and then it's 6s2. You completely fill out the 4f, 14, and then we go to the 5d. And we have 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now, platinum 2, we don't have this. So we have basically, we're looking at, for my d electrons, we're looking at 8 electrons because we're looking only at the d orbitals. Okay. And remember, for platinum 2, you lose your valence electrons first. So if I fill up platinum 2, it'd be 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the chlorides here, you're not going to, this is very high energy. So your electrons, when you fill it up, will be all of the other possibilities, not the highest energy one. Okay, so let's do another example, and then we'll move on. So, another example is this. Turns out that when we look at nickel, Okay, so when we look at nickel, so this is my tetrachloro nickelate 2 ion. This is paramagnetic. Okay, if I look at my tetracyanonickelate 2 anion, this is diamagnetic. So the question is, which is square planar and which is tetrahedral? So in order to do this, what we need to do is we need to know the number of d electrons. So one, we have to determine the number of d electrons in nickel 2. Okay. And then 2, we need to fill the d orbitals for square planar and tetrahedral. Okay? And once we do that, then we can determine which is diamagnetic and which is paramagnetic. Once we do that, we now know the answer. So, how many d electrons then are in nickel? So, nickel 2. Nickel has 28 electrons, and nickel itself is argon. Okay. 4s2, 3d, you can see that, 8. Alright. So, nickel 2, then that is argon 3d8. So we're going to be working with 8 d electrons. So now, let's draw our square planar and our tetrahedral d orbitals once with the ligands. Okay? So tetrahedral we had basically my T2 set and my E set, okay, and basically delta is small. So this is my d orbitals, right? If we look at square planar, then my ligands are at the x-axis and the y-axis, then it's going to be my dxz and my dyz. Okay, look good. Then it's going to be the dz squared. Okay, and then it's going to be what? The dxy, because it's not directly on my axis, and then dx squared minus y squared. All right, so let's fill this out. 8 electrons. So nickel 2 has 8 electrons. 8 d electrons. D orbital electrons. Let's be specific on that. So I have 1, 2, 3, 4, 5, 6, 7, 8. Okay? This one I have 1, 2, 3, 4, 5, 6, 7, 8. So if you look at this, all my electrons are paired. Therefore, this one, the square planar, is diamagnetic. Two below so you can have space. Diamagnetic. Okay? My tetrahedral, I have 2 unpaired electrons. So this one is paramagnetic. Okay? And if we go back, it turns out that the tetrachloronickelate 2 ion is paramagnetic. And it says that my tetracyanonickelate 2 ion is diamagnetic. So now, since I know that this is diamagnetic, we know that this one is square planar, and we know this one will be tetrahedral. So knowing the properties, we can actually go back and revert to the other ones. Okay? So, this is how we actually use crystal field theory in order to predict the physical properties, like the magnetic properties. When we look at the color wheel and we're looking at the difference in our delta, then that allows us to determine actually the colors. So knowing what ligand and how much the delta is, and we know how much the delta is, and we know if it's a weak field or a strong field ligand, and we can actually, using the color wheel, determine what wavelengths are absorbed and then what color that solution should appear. Okay, so this is going to end our topic on our transition metals and transition metal complexes.